This is designing a fuel handling system for emergency generators the preferred way. I'm the presenter. I'm David Oaf. I am a mechanical engineer who has worked in the boiler industry since about 1990 and worked for Preferred since 2006 doing fuel handling systems, which is what we're going to talk about today. If you have any questions about what we're doing, go ahead and email me at the address on your screen, deoff@preferred-mfg.com, and we will answer your questions right away. If you think your question might be location specific, let me know where you are at, and I'll refer your question to the preferred person in your area. And as you're going to see in this presentation, some fuel oil codes vary by region. So sometimes the answer to your question depends on where you're asking it from or where the job site's going to be. So with all that out of the way, we're going to get started. First off, we define the requirements for a successful fuel handling system. We need to reliably supply fuel to all the connected generators. We need to prevent overfilling a tank and causing a spill. We need to detect leaks and provide the appropriate responses. We need to communicate important information to the facility, and we have to adhere to all national, state, and local codes at a minimum. The codes we follow are NFPA 30, NFPA 31, NFPA 37, NFPA 110, and local fire codes. And for most fuel oil handling systems, the authority having jurisdiction is going to be your local fire marshal. I work in the Dallas area, so I contact the Dallas Fire Marshal and the Fort Worth Fire Marshal, and both offices have people that are very helpful. So before we start designing the fuel system, we need to know what we're up against. We need to find out, are the main tanks above ground or are they underground? What is the configuration of the main tanks? Are they horizontal, vertical, cylindrical, rectangular? Do the tanks need to be UL 142 or do they need to be UL 2085 fire rated? And then finally, what size are the main tanks? This is a picture of a cylindrical underground storage tank. Underground storage tanks, or USTs, can hold a lot of fuel, more than an above ground tank. They don't take up any real estate because you can put parking spaces on top of them. Installation requires special licenses, so they're more involved to install. More agencies claim jurisdiction over underground tanks. I have a customer in Austin, Texas, and 4 different agencies claim they have jurisdiction over his underground tank. Preferred doesn't manufacture main tanks, but we can include them in our projects, and when we do, we'll make sure the main tank is coordinated with the rest of the fuel supply system. Here's a picture of a rectangular above ground storage tank. Rectangular above ground tanks are easier and cheaper to install. Leak detection and virtually everything else is easier with an above ground tank than with an underground tank. They take up space and they're ugly, so architects usually favor underground tanks over above ground tanks. And for most mechanical engineers, the choice of tanks has already been made by the time we get the project. And it's usually the architects that are deciding where the tanks are going to go based on available space, and we have to live with their decisions. If the size of the main tanks hasn't been determined yet, you may need to use the preferred fuel load calculator. In the fuel oil calculator, you input your generator sizes, the required run hours, a couple of things like ullage and drop tube gap, and it'll calculate how many gallons of main tank storage you need. Florida recently passed a law that said that nursing homes have to have 120 hours of fuel available to their generators. So this is getting used a lot in Florida. You can find the preferred fuel load calculator here at this URL, or just Google preferred fuel load calculator and it'll be our first hit. This little web tool is so easy, it doesn't really require any explanation. So, more things we need to know about system. Where are the generators located in relation to the main tanks in terms of vertical distance and pipe length? By now, you should know whether the generators are going to be on the ground floor, whether they're going to be up a couple of floors, or whether they're on the roof. And we should know whether our main tanks are going to be above ground or below ground. We need to know if the generators are going to be supplied with belly tanks or if the fuel system supplier is going to need to provide day tanks. And then finally, we're going to need to know the capacity of the generators. This is a typical generator belly tank. Belly tanks are convenient because they can be ordered with the generator and don't add to the generator footprint. At Preferred, we don't like belly tanks because they're often not deep enough for the float switches we need. The tank shown in this picture looks to be about 6 to 8 inches deep, and we need to fit at least 4 float switches in that tank of different levels. So these short tanks can become a problem. Access to belly tanks can be difficult because not shown in this picture is going to be a diesel engine on top of that tank. So getting to the float switches and level controls can be like working on a front wheel drive car and no fun for anyone. Belly tanks are often supplied by the electrical contractor. So coordination issues are often common because the fuel system will be supplied by a plumbing contractor or a mechanical contractor. This picture shows a typical Preferred day tank with rupture basin. Day tanks tend to be tall and skinny to reduce their footprint. And the disadvantages I talked about with the belly tanks just don't exist with the day tank because they're made for access. They're made to be tall. We can get all 4 of our level switches into one device. Generators and belly tanks are typically sized for 2 to 4 hours of generator runtime, but some authorities having jurisdictions will put additional limits on the amount of fuel you can store in a day tank. Los Angeles, for example, limits day tanks to 60 gallons. So with a large generator, you're obviously not going to get 2 to 4 hours worth of runtime. So the first step in supply pump sizing is determining the consumption of the generators. There's a real easy rule of thumb to help with this. For every 100 kilowatts of generator capacity, the engine will consume 7 gallons per hour of diesel fuel. In this example here, it's an 800 kVA generator, so 800 kilowatts and 56 gallons per hour. So on top of that 56 gallons per hour, we're going to want to apply a generous safety factor, usually 3.0 to 4.0. The idea here is we want the supply pump to come on, quickly top off the day tank, and cycle off again. The pumps for most generator fueling systems are relatively small, so even with a large safety factor like this, the safety factor may bump you up from a 3/4 horsepower to a 1 horsepower pump. It's not a huge increase in pump horsepower, cost, or electrical consumption. Preferred provides positive displacement pumps for 50 psi discharge and 100 psi discharge. This table is from page 38 of Preferred Utilities Catalog 25. This catalog is available online. If you want a hard copy, email me and we'll make sure that you get one. These are the pumps used in Preferred's ATPS and SATPS pump sets. ATPS stands for Automatic Transfer Pump Set, which is the packaging that we typically use with generator fueling systems. The SATPS is a semi-automatic transfer pump set. The pumps and the piping are the same. The difference is the semi-automatic pump set is usually used for boiler systems, and the controls are much more stripped down compared to the ATPS. But as far as pump sizing, they're exactly the same. We keep the parts for each of these pump sets in stock. So if we get a rush order, we can usually put together one of these pump sets pretty quickly in a matter of a couple of weeks. So, if you're not sure what your pump discharge pressure will be, we have a handy web app called the Preferred Pump and Pipe Sizing web app. With this web app, you put in your configuration, whether the tank is below the pump, as in an underground storage tank, or whether it's above the pump in an above ground storage tank. You put in your line sizes, you put in your valves, you pick a pump from a drop down menu, and this web app will tell you in real time what your pump discharge pressure is and what your pump suction pressure is. As long as you're good, those numbers stay in the green. If you get marginal, those numbers will turn orange. And if you get into a situation where the pumps just aren't going to work, this will turn red. And there's usually a note down there to give you an idea of what you're doing wrong. Suction line sizing is critical with positive displacement pumps because they're limited to about 20 inches of vacuum. Discharge pressure is less critical because we have 50 or 100 psi to work with, which is a lot, but it still needs to be checked. You can find the Preferred Pump and Pipe Sizing web app here at this URL, or just Google Preferred Sizing Calculator and it should be the first hit. In the pump and pipe sizing program, there's a pull-down menu where you select the pump based upon the sizing calculations we did before. Start with a 50 psi pump. If you are in a situation where the day tanks are a long ways above the pumps, you may find that you need to go to a 100 psi pump. In a properly designed fuel system, most of your inlet vacuum and discharge pressure will result from vertical lift, the hydrostatic pressure of the oil, not from piping losses. So we need to watch very carefully on underground tank systems, the diameter of the tanks, how deeply buried the tanks are, and then how high above grade level the pumps are going to be mounted, because we're up against a hard limit of about 20 inches of mercury on the suction side. If you're in a high-rise application and you're certain you haven't undersized any of your piping or valves and your discharge pressure is still above 100 psi, that's probably an application for rotary screw pumps. Contact somebody at Preferred and we'll set you up with information on rotary screw pumps that can go to much higher discharge pressures. There's a lot of text on this page, but it really boils down to just a couple of things. We've already determined the flow rate in gallons per hour of our pumps, so we use the pump and pipe sizing program to make sure that our suction conditions are going to work for the positive displacement pumps and make sure that our discharge conditions aren't going to overcome the maximum output of the pump as well. Now that you know which pumps are the best selection, you can refer back to this chart for more information about that pump set, including pump RPM, pump horsepower, whether that pump motor is available in single phase or three phase, dimensions, and then the connection sizes for that pump set. This is on the Preferred website, and you'll also find AutoCAD drawings of these pump sets on the website. And if you email us, we can send you SolidWorks models of these pump sets as well. So now that we've determined our pump sizing, it's time to start designing the piping layout. We're going to start at the suction side. What's shown on this screen is a typical suction piping diagram for a duplex pump set with an underground storage tank. For simplicity, we're not showing all the ball valves, pressure gauges, and other piping details that are part of the pump set. Note though, we're showing two Y strainers upstream of the pumps. That's the base model. These pump sets can also be provided with a duplex basket strainer that allows you to dump and clean one basket while you run oil through the other basket. It's a -D behind the part number of each of these pump sets. There's an important item in the main tank. That's the foot valve. The foot valve is like a check valve that prevents oil from running backwards through this line and evacuating the oil pipe between the pump set and the foot valve. The number one problem with positive displacement pumps is that they can lose prime if this suction piping isn't done correctly. Note that we show the supply and return pipes on opposite sides of the tank. This is good practice to keep the tank contents well mixed. This is a typical suction piping diagram for an above-ground storage tank. You'll notice it's exactly the same, except we've added an anti-siphon valve. Many people are tempted to use a solenoid valve in place of the anti-siphon valve. You can't. A solenoid or motorized valve doesn't serve the same purpose as an anti-siphon valve. An anti-siphon valve is designed to stop the flow of oil if there is a major leak or a break in the line below the oil level in the main tank. The anti-siphon valve is similar to a spring check valve. The spring is sized so that the pumps can overcome the spring force, open the valve, and allow oil to flow. Siphonic action, or the difference between the hydrostatic pressures of the two columns of oil, will not open the valve, so there is no oil flow. Anti-siphon valves are often required by local codes. And their CVs are relatively small. So if you're using the pump and pipe sizing program and you keep coming up with a lot of pressure drop in your suction line, you may need to oversize the anti-siphon valve. So what do we do if we have multiple main storage tanks? We're going to add tank select valves to the suction piping. As you can see, multiple main tanks are piped in parallel. The shutoff valves are called tank selector valves. They can be manually operated or automatically controlled by the preferred pump controls. Because the most common cause of overfilling a tank and causing a spill is human error, Preferred likes to automate the tank selector valves. The little I in the diamond stands for interlock, meaning the action of that valve is interlocked with the pump controls and the high-level switches in the main tanks. So moving on to discharge piping. Discharge piping between the pump set and the day tank is very simple if there's just one day tank. The flow switch is there for the pump set lead lag function. If we energize a pump and don't prove flow, we will energize the alarm, shut off the lead pump, and energize the lag pump. If the lag pump doesn't prove flow either, we shut off both pumps and keep the alarm energized. The controller in the ATPS pump set speaks Modbus, Ethernet, and BACnet, so the facility can know everything the pump set controller knows. Typically, the Modbus address registers that are mapped out to a building automation system include allowing the facility to know when the common alarm is energized, when we detect a leak, and when a pump is running. There's a lot more Modbus addresses than that, but those are the most common ones that are actually used by the building automation system. We're not done building the piping diagram. After we do the supply piping, we need to include a return line. In the schematic shown on this screen, the day tank is located above the underground storage tank, so our return line can be a simple gravity-powered overflow line. If you're going to specify gravity return, ensure the routing of the return line will accommodate gravity return. Horizontal piping must be downward sloping, and there can't be any up and overs in the piping. Typically also, the return line size is one pipe size larger than the supply piping. You always want to be able to take fuel out of the day tank faster than you can put fuel into it. New York City is now requiring you to provide your sizing calculations for gravity return lines to ensure that they will work. This is a new requirement we just started seeing about a year ago. With an above-ground main tank, we can't use gravity, so we specify a return pump mounted right on top of the day tank. If the oil level in the tank reaches 90% or higher, the return pump comes on and brings the oil level down to a normal level. The return pump must be able to pull more oil out of the tank than the supply pumps can supply. Preferred uses return pumps even when gravity return will work for a few important reasons. Commissioning of the system goes faster because the technician can empty day tanks and fill them back up again and prove the operation of the system. After the system is commissioned and turned over to the owner, the facility's operators can periodically test the fuel supply system by putting a return pump in hand, drawing the oil level down to the pump on switch, and seeing that the supply pumps come on automatically and top off the day tank. This is a good thing to do weekly, monthly, and definitely if you think you're going to need to run your generators like you're in Florida and there's a hurricane out in the Gulf. When combined with main tank filtration, we'll often supply return pumps so that all the fuel in the system can be polished. Preferred filtration systems typically will pull out of the main tank and return to the main tank, but that doesn't clean up the fuel in the day tanks, and it's the day tank fuel that the engine's going to see first. So we'll often combine the operation of the filtration system with the operation of the pump set so that we can pull the oil out of the day tanks, make sure it gets cleaned, and then put back into the day tanks with clean, polished oil. And then finally, in hot climates, we'll sometimes use a return pump to do what we call level bouncing. The diesel engine uses the fuel for cooling, so the fuel that comes back to the day tanks is hot. In a hot climate like Texas, that oil can get so hot that it starts to derate the capacity of the engine. In that situation, we'll put a thermocouple in the day tank to sense the temperature of the oil. If the oil level gets above set point, we'll energize the return pump and start pumping hot oil out of the day tank and let the supply pumps come on and refresh that oil with cooler oil out of the main tanks. This is something we do in Texas and Los Angeles in particular. Multiple day tanks are piped in parallel, just like multiple main tanks are piped. The supply pipe common to all the day tanks is called the supply header. The supply header can support virtually any number of day tanks. The largest system that Preferred has done included 11 main tanks piped in parallel, and as of now, 28 generators all piped in parallel. And actually, that system had duplex supply headers and duplex return headers so that there was no single point of failure that would keep fuel from getting to the engines. When we have multiple day tanks in a system, we need to include fill valves in the system so that only the day tank calling for fuel gets fuel. So going back a couple of slides, this was our suction piping diagram for two main tanks. When we add return piping to the system, it gets quite a bit more complicated. The return piping is headered just like the supply header, so that in theory, any day tank can pull from any main tank. Some customers specify that flexibility. Other customers will only return to the tank they're drawing from. This is a safer alternative because when you pull from one tank and return to another tank, you introduce the possibility of overfilling that tank. If your customer is okay with drawing from one tank and returning to the same tank, we can simplify the piping quite a bit using a preferred tank selector valve. They're shown here in both threaded and flanged versions. These are 6-port valves that include a common, a normally open, and a normally closed port for both the supply and the return lines. So you never have to worry about your valves being lined up. They're available with lever operators, as shown in these pictures, and we can also supply them with motorized valve operators with proof of open and proof of closure limit switches if you want to automate this function. So getting back to the fill valves, it's never as simple as what we've shown you already. In real life, the fill valve is part of a larger flow control manifold. The most basic flow control manifold consists of a solenoid shutoff valve with a 3-valve bypass around it. The 3-valve bypass allows the operators to isolate a day tank, isolate the fill valve for maintenance or replacement, or bypass the fill valve to automatically fill a day tank. Excuse me, you can bypass the automatic valve to manually fill a day tank. When Preferred does these systems, we interlock the supply pumps with the high level switches in the day tanks so that even when a facility operator has bypassed the fill valve, they cannot overfill the day tank. There's a reason for everything we do at Preferred with these fuel handling systems. It's like my first marching band parent meeting before a big overnight bus trip. The band director told us some of these rules I'm going to go over are going to sound bizarre, but believe me, there's a reason for every one of them. And coming from a boiler background and now working on these fuel handling systems, I've found the Preferred engineers don't do anything by accident. There's a reason for everything they do. So, a common thing to add to flow control manifolds is another solenoid shutoff valve. The logic for the second solenoid valve is usually driven by the leak detector in the day tank rupture basin. If the leak detector detects a leak, it cuts power to the solenoid valve and that solenoid valve closes. It's usually independent of the other pump control logic. Some mission critical customers ask us to provide systems with different logic. They tell us to sound an alarm when a leak is detected in the day tank, but keep providing fuel to the generator. We will often include an inlet strainer in the flow control manifold. This is to keep chunks of oil from going through the line that could potentially foul the solenoid valve and keep it from fully closing. There are higher quality filters between the day tank and the diesel engine. This strainer is mainly to keep chunks out of the solenoid valves and out of the day tank. We will often provide a flow switch in the flow control manifold. If we prove oil flow out of the supply pump, but no flow is detected at the day tank, alarms should sound and people should start running. So in this scenario where flow is proven at the pump set, we've energized fill valves, but no flow is proven, it means one of three things. Someone closed one of these hand valves, so the day tank isn't going to get fuel. A solenoid valve didn't open, either because it burned up the coil, blew a fuse, or any one of the million reasons why a solenoid valve will quit working. Or there could be a massive break in the supply piping between the two flow switches and fuel isn't getting to the day tank, it's getting poured onto the ground. These are all situations where we want to sound the alarm and get a facility person out to investigate. And this is also why we say to have 2 to 4 hours worth of fuel in your day tanks. If your generators are commanded to run and there's a problem with your fuel delivery system, if you've got 2 hours worth of fuel right there at the generator day tank, that gives you time to correct some sort of a problem that's going on with the fuel supply system. Sometimes we'll put a flow meter in the flow control manifold. It basically does the same operation as the flow switch, and we don't recommend it, but it's specified sometimes. A site flow indicator can be very handy in the flow control manifold. When we put oil into a tank, we're going to run the pipe all the way down to within 6 to 8 inches of the bottom of the tank. We do this to prevent splashing or foaming of the oil. Foaming of the oil can make the float switches work poorly, and if we have some sort of a level sensor inside the tank, foaming or waves on the top can interfere with the level sensor. So there'll usually be a pipe that goes down to within a few inches of the bottom of the tank. Because of that pipe, you're not going to be able to hear oil splashing into the day tank. So it's nice to have one of these sight flow indicators so you can actually see the oil getting to the day tank. Some of our higher end customers will specify motorized shutoff valves instead of solenoid shutoff valves. Motorized valves are much less likely to leak by, they're more reliable, and they can be supplied with proof of open and proof of closure switches for our really paranoid customers like our data centers. If money was no object, all of our day tanks would be provided with motorized fill valves, but they are very expensive compared to solenoid valves. But we're only supplying fuel to generators, powering server farms, operating rooms, respirators, emergency lighting. So,
Josh, call 1603, please.
sorry, we won't get any more pages. Okay, so going back to the fuel control system, we've drawn the diagrams now. The next thing we're going to do is we're going to explain how the pump controls work. In a typical sequence, when the engine draws the fuel level down to 50%, that's the pump on level, the lead supply pump will come on, the fill valve will open, and it'll top off the tank back again to the 80% level. This is one of the reasons why we tell you to put a fairly high safety factor on your supply pump sizing, because you want this topping off of the tank to go fairly quickly. There's a job in Florida right now where the engineer sized the supply pumps for the generator consumption, put about a 25% safety factor on the supply pump side, and then found that the belly tank was a 2,500 gallon tank and takes 16 hours to fill from 50% to 80%. So the safety factor is not large enough, and when the generator is running, supply pump runs virtually all the time. We don't want the supply pumps to see a duty cycle more than about 25%. So that's why you'll see that safety factor of 3.0 to 4.0. So there are a few what ifs in this pump control strategy. What if the oil level gets down to the 40% critical low switch? Preferred will sound the alarm and energize the lag supply pump, and now you've got two pumps working to top off this tank. What if the oil gets up to the 90% critical high switch? In that instance, we sound the alarm, interlocks kick in to de-energize the supply pumps and the fill valves, and we energize the return pump. Remember, one of our reasons for specifying return pumps was to test the system. When the day tanks have return pumps, the preferred technician will run through these what ifs multiple times. He'll run through it multiple times with the customer watching so that you can see that the system works like it's designed to work and is going to work in an emergency. So there's a few variations on that basic control strategy. Sometimes that 4-position float switch that we call a PLS4 can be supplied with 5 or 6 float switches. The additional switches can be an additional high-level switch, it can be an additional low-level switch, or it could be an emergency low-level switch that will turn off the generator if the level gets too low for the engine to suck fuel. Sometimes when a tank is not very tall, like a very short belly tank, and there's no room to put that critical high switch in the tank, we'll put that critical high switch in the tank vent line so that if we start to push fuel up the vent, this switch goes off and we'll shut off the fill valve and shut off the supply pumps and energize the return pump just as if the switch was in the tank. Another common request is that instead of a duplex pump set, we'll supply a triplex pump set to give you 3 possible pumps and motors to run in an emergency. And then sometimes instead of just one return pump, we'll supply duplex return pumps. And a flow switch and the lead lag logic works just the same as the supply pumps. So moving on to leak detection. Leak detection is required in tank interstitial spaces and in containment piping. Virtually all main storage tanks and day tanks now are required to be double wall with some sort of leak detection in the interstitial space. What we've shown here is 2 of the float switches that Preferred uses. On the left is our PS LDS leak detector and our RBS leak detector. The RBS stands for rupture basin switch because we typically install this in the rupture basin of a day tank. And these are just float switches. Very simple. Preferred pump sets can be provided with optional leak detection in the rupture basin. There's a bunch of fittings in a pump set. It's a good place for a leak. There are also lots of unions that don't always get tightened up. So it's not a bad idea to put a float switch in that rupture basin to let you know when fuel's accumulating in the rupture basin. Then a word about threaded piping. The pump sets at Preferred were pressure tested and vacuum tested at our factory prior to shipment. Then they bounced down the road several hundred miles on poorly maintained highways, and it's not uncommon for the piping to leak when it gets on site. So it needs to be tightened up, especially things like unions. The same is true of the terminal blocks in the control system. The terminal blocks were tight when they left the factory, but they can loosen up on the truck. And when you've got a wire sitting in a terminal block and the terminal block isn't tightened down all the way, it can make an intermittent contact that will drive a technician crazy because sometimes it'll work and sometimes it doesn't work. So a smart thing to do is before you even start setting up a new pump set or a new boiler or two, tighten down all the terminal switches, again, terminal blocks, and give them all a pull test to make sure everything's tightly tightened down. In some places, you may need to use a discriminating leak detector. What's shown here is a Preferred HDA2C. It has both an optical sensor and a conductivity sensor. So when the optical sensor sees some sort of fluid, it looks at the conductivity sensor. If the fluid covering the sensor conducts electricity, it tells you you have a water leak. If the fluid does not conduct electricity, it reports it as an oil leak. This is commonly used in the interstitial of underground main storage tanks. A water leak indicates a breach in the outer wall. An oil leak indicates a leak in the inner wall. If a leak is detected, in most cases, the Preferred controls will sound the common alarm, de-energize supply pumps, and close fill valves. In some mission-critical facilities, the Preferred controls are programmed to sound the alarm, but pump controls stay in normal operating mode. The idea is these facilities are so critical that even in the event of an oil leak, they don't want to take fuel away from an emergency generator. Leak detectors can be wired into the tank gauge or they can wire directly into the pump control system. With Preferred systems, the tank gauge and the pump controls communicate electronically, so it might be designed either way. So finally, tank gauging. All main tanks require electronic tank gauging. Some customers want tank gauges in their day tanks as well. In most jurisdictions, if the truck driver can't see the tank where he's putting fuel into, you're going to need a tank gauge with an overfill system that can alert the remote truck driver to when he's starting to overfill the tank. In Dallas here, it's part of the inspection process. The fire marshal will come out and you order a truck at the same time and you'll fill up the tank, and the fire marshal wants to see the alarm and the horns go off at 90%. So what's pictured here is the preferred fuel sentry tank gauge. This is a tank gauge that can be used for 1 or 2 tanks and comes with an optional onboard printer. Shown on the left in this slide is the flush mount version. We can include this tank gauge as part of the pump controls on an ATPS pump set. And what's shown on the right is the wire float level sensor. Preferred offers 3 types of level sensors. The most common type of level sensor we provide is the wire float level sensor. We'll use this in virtually all of the main tank gauging we do. We also offer head level sensors and ultrasonic level sensors that are more often used in day tanks, but they can be used in main tanks as well. The head level sensor is basically a differential pressure transmitter. The high sensing line for the differential pressure transmitter is a stainless steel torpedo-shaped device that hangs down at the bottom of the tank, as shown in the middle diagram here. Because it's a differential pressure transmitter, it needs to have a negative side to it, and that negative side runs through the cable, through the conduit, and then goes to what we call a barometric compensator, which is just a little device to protect the end of that tubing and try and keep it clean and bug-free. The ultrasonic level sensor is basically a fish finder. It's mounted on the top of the tank, sends a signal down that bounces off of the oil in the tank and lets you know the distance between the sensor and the reflected oil. The ultrasonic level sensor comes with software where you can put in your maximum tank height, your mounting height, and a couple of other parameters, and it does a little bit of math to determine then the level of the oil in the tank. All 3 of these level sensors report back the level of oil in the tank. The conversion from inches of oil to gallons of oil is done in the tank gauge. And with the fuel sentry tank gauge, the common varieties of tanks are included in the software. So things like horizontal cylindrical tanks, vertical cylindrical tanks, those are all accommodated in the software. If you have a tank with unusual geometry, the fuel sentry includes a 50-point stick chart that's like a 50-point lookup table where you can put in the actual gallons of the tank that correspond to each of the inches of oil in the tank. So that was a basic introduction. For next time, we're going to cover fuel polishing. When is fuel polishing needed and what's the best way to go about it? We'll talk about high-rise fueling applications. We'll talk about applications that involve fuel oil heating in cold climates. And we'll expand on the oil cooling strategies we talked about a little earlier. We'll go through some real-life design examples. And then we'll look at a couple of case studies where things went horribly wrong and how that could have been prevented. Again, if you have any questions about what we went over, or you want us to send you a hard copy catalog 25, or you want to contact us, our phone number is there and my email address is there. If you have a question about a specific fuel system in your territory or in your location, send us the location and I'll make sure that your question goes to the nearest preferred person who will be up to date on the codes in your region. And that's it. I thank you very much for attending. We will probably do something like this every 2 to 4 weeks. Check out Mr. Bond's LinkedIn account. We will be publicizing future webinars on his account. Thank you.